All right, so all of these problems start with Newton's second law because we need to have an unbalanced force. And that unbalanced force has to be a centripetal, or has to provide a centripetal acceleration. So in this case, there's a force on the moon from the Earth. And of course, there's a force on the Earth from the moon. This is the gravitational force, the one we talked about yesterday. And before we get into this too much, the force that we calculated yesterday, this Newton's law of universal gravitation, we didn't do much with it because it's pretty big and getting it into the calculator can take a little bit of time. But this is Newton's law of universal gravitation. You'll notice it has two M's in it, but the force that we have here acts on both objects. It's a Newton's third law force, which means this force pulls on the moon and the Earth with the same amount of force. This force is more effective on the moon because it's smaller, but it actually is pretty effective on the Earth. It causes the Earth to wobble. In fact, the Earth actually orbits the moon a little bit because this force acts on both objects, and therefore both objects experience an acceleration. So I want to be really clear, you're easy to trick on multiple choice, but the force on the moon is the same as the force on the Earth. And this is true for any two objects that are experiencing a gravitational force. Now, we're going to focus on the moon, but I want you to understand that there's actually more going on than what we're going to talk about. It's more complicated than this. If you want to really get into the complications of this, you have to understand that they actually orbit about their center of mass, which is right about here. And the whole thing wobbles on its axis because it's going around the sun. And the whole thing is experiencing tidal forces from the other planets. It's more complicated than this. This is why it's hard to find out if that asteroid's going to hit the Earth or not. There's things out there we just don't understand and don't always know. So although we're going to talk about simple circular orbits, the reason why it's hard to go into space is because there's more than just the simple stuff happening. Okay? So we're going to talk about simple orbits. And that means I'm focused just on what's happening to the moon. So the first thing I want to tell you is that we are dealing with an object that is in centripetal motion. So the first thing we do is we change our acceleration to v squared over r. Now in your notes, there's a few things you should probably, make sure you have down there. This is the separation distance. And it's the radius of curvature. That capital R stands for both. In Newton's law of gravity, it's not the radius of curvature, it's the separation distance. In the centripetal acceleration, it's the radius of curvature. So in this problem, we're assuming they are the same thing, that the radius of curvature is also the separation distance between them. That's not always true, and you need to start every problem by figuring out if that's true or not. It is not uncommon for them to give you the altitude in a problem. The altitude isn't the separation distance. The altitude is how far above the surface of the Earth we're talking about. That's an altitude. You can't use the altitude. So if you're given the altitude or you're asked about the altitude, you'll have to add the radius of the Earth to it. So don't be tricked by something like that on a problem. When we're talking about this formula, is from the center of one object to the center of the other. So make sure you write that in your notes and have a reminder, because that will make, it'll make mastering a little bit easier for you, I think. Noah's joining us a few minutes late. Let's all welcome Noah to class at 8:45. He's here right about now. Good morning, Noah. guess he's being quiet this morning. I'm not gonna wait too long to see if he'll say good morning.
Hey, good morning. Sorry, my computer like just crashed. I've been here the whole time.
Okay, I'm sorry. It's hard to know. It's a big list. So back to work. Get all that out of the way. Get all this out of the way. Now, the next thing, this velocity that's here. This is the tangential velocity. It's how fast the moon is going sideways. Now, the idea here is what's actually happening is the moon is traveling to the side, just like I have it pointed in the picture. But the force of gravity is causing it to fall towards the Earth. And so that's what creates this circular path. An orbit occurs when it's falling at just the right rate to curve around the Earth, like so. If the moon goes too slow, it'll curve into the Earth and hit it. If the moon goes too fast, it'll fall away from the Earth and be gone. An orbit is the perfect balance, where the force of gravity provides just enough pull to cause the object to fall always, to continuously fall around the planet. So it's always being pulled towards the planet, but it's kind of moving sideways fast enough to avoid hitting the planet. It's doing that all the time. You balance it just right, you get an orbit. You balance it wrong, and you have a problem. Now, the truth is, it's balanced wrong. The moon is actually flying away from the Earth. Every year, it's a little bit farther away. Although this won't affect us in our lifetime or your children's lifetime or your children's children's lifetime, every year the moon is a little bit further, and it's measurable. We put reflectors on the surface. I say we, sound like I did it, but reflectors are placed on the surface of the moon, and we can precision measure its distance away from the Earth. And every year it measures a little bit further away. So the moon is just drifting a little further away. It's going a little too fast to stay in the orbit that it's in. But that doesn't change what we have to do for our work. I just thought that was an interesting little tidbit of knowledge so you can be a little bit smarter when somebody asks you about the moon. So that's this side. Now, the other side is the net force acting on the system. For that, we're going to go to Newton's law of universal gravitation, which is going to be m1, which is the mass of the Earth, m2, which is the mass of the moon, g, and that separation distance squared. So an orbit occurs when the force of gravity causes a centripetal acceleration. And that's what that means. Now, there's one nitpicky little thing, a detail that is probably more important than it seems. Which m is this one? And don't be fooled. That m, that has to be the thing that's in orbit. So when you choose which m to put there, that's the one you're focusing on, the one that's going around in the circle, the one that's in orbit. So in this case, this is going to be the mass of the moon, because that's what's going around in the circle. Now, the first thing that you should notice is that it doesn't matter what's in the orbit. That happens every time. So whether we're talking about something as big as the moon or as small as a pebble, they both have to have the same speed if they're going to be there. But the mass of the object doesn't matter. The mass of what's at the center matters. So the thing that's being orbited, that mass matters. The thing that's doing the orbiting doesn't. So if they don't give you the mass of the thing that's in orbit, don't worry, it's going to cancel out. So whatever we put into orbit, we don't need its mass for calculating how fast it has to be going in orbit. And that's the next thing. This is the most important detail today because it's going to help you understand what you can get from this and what you can't. All this can actually tell you is either where the orbit is, r, or how fast the object is going to be going. That's all it can really tell you. So when we talk about an orbit, that's the only two things that we can really find. Now, it could be other stuff. They could say that you're looking through your telescope and you see a planet with moons around it, and you want to figure out the mass of that planet by watching the moons. You can do that too. That's how we figure out the mass of planets that we see in our telescopes, Jupiter's mass and stuff like that. We watch the orbit of objects around it, and that's how we determine their mass. So it has properties, but we're talking about calculating the orbit. So most of the time we're worried about calculating V. How fast does the object have to be traveling? But I'm going to digress a little bit because there's two things about this that are unusual until they're spelled out for you. First, remember, when the object is in orbit, it's traveling at a constant speed. The speed is a constant. And the speed is very predictable in that the speed is going to be how far it has to go divided by how long it takes. When they start asking you what the period of the orbit is, they're talking about this. Since it's in a constant speed, we can figure out how fast it's going by dividing how far it goes divided by how long it takes. That's this. Because it's traveling in a circular path, the path it travels in is a circumference. And we use a capital T for what we call the period of revolution. Sometimes called the period of oscillation. Anything that repeats itself, we call a period. The time it takes to repeat is that period. Capital T is generally the term used for a period. And when we're talking specifically about an orbit, it's the period of revolution. So if your problem asks you how long it's going to take to go in that orbit, they're asking for this T. So I hope you see that you're going to either have to find out what the velocity is first and then use it here, or if you're feeling very adventurous, you can combine these two things into one relationship that'll get you the period. Now, one of these is probably going to be scarier for you than others because right now there's already a lot on the page. So what we're going to do is this. We're going to figure out what the velocity of the moon is. And I want to do that because we can do that with what's sitting here in front of us, meaning we can take this and figure out the velocity of the moon. Now to do that, you're going to need a few things, I think. What's one of the things you're going to need?
The mass of the Earth.
Yeah, I gave you that yesterday, but let's go ahead and again today, 5.97 times 10 to the 24th. That's in kilograms. And what else are you going to need?
The radius of curvature.
Right. And for this case, this is the Earth-Moon distance. And although I thought I had written it down here in front of me, apparently I took that piece of paper off my desk. So I need to find the Earth-Moon distance.
I have it on the mastering. It's 3.8 times 10 to the 5 kilometers.
So 3.8 times 10 to the 8th meters. We need it in meters. So the Earth-Moon distance, you said 3.8?
Yeah.
So if they gave it to you in kilometers, you're going to have to put it in meters because everything we have is in meters. So first, I hope you notice that there are some things you can do to reduce the work you have here. One of the R's will cancel out here. And that's going to leave you with something like this. Now, a lot of big numbers, square roots and all. Everybody give it a go. You've got to put those numbers in your calculator and you've got to give it a try. So everybody give it a go and put your value for the velocity in the chat, please. All right. Looks like everybody's getting that. Good, good, good. Pretty fast. Believe it or not as fast as like the space station is going right now. Slower because it's further away from the Earth. I want you to also think that if we look at speed, that is about 3 times the speed of sound. It's about as fast as a bullet traveling from a rifle. So when you think about the fact that we landed somebody on there, they had to land on something traveling faster than a bullet, but as big as the moon. Doesn't sound like much, but I can't imagine being the person who said, oh yeah, I can do that. That's pretty fast. So now that you have that velocity, this screen on my computer is just really full of numbers and stuff. So I'm gonna try and make it a little bit smaller, put it off to the side. This is the tangential velocity of the moon, which is pretty fast. But if we want to figure out how long it takes to go around the Earth, that's when we have to use this, which means we set this equal to 2 pi r over the period. And this will figure out the period for us. Now, our answer is 28 days, but you'll find that when you figure this out, you're not going to get 28 because our answer is going to be in seconds. So you're not going to like the next thing I'm going to tell you, but on your next test, we're going to have an orbit question. And on that test question, I'm going to ask you to put the time in the most reasonable unit available, meaning you're going to get some number that's in seconds, and you're going to have to keep converting it until you get something reasonable. And I won't tell you what that is, days, hours, minutes. You'll just have to keep making it a different number until you get one that you can compare to something. Because if you get 400 hours, that doesn't mean anything to me. But if you get 6 days, that means something. So you keep converting it until you get the smallest number that makes sense for the unit. Now, what I'd like to do is twofold. For those of you who you're not having difficulty with this, I'd like you to stay with me for a bit of a conversation. For those of you who are just barely hanging on, I want you to take this and find the time and convert it to days. But you guys who are following along with this with no difficulty, I want you to consider what you would do if you wanted to come up with a single relationship that you could use to calculate orbits. Because there's something kind of hidden in here. And you guys who are like mathy math might appreciate this. What I'd like to do for you guys is we're going to take and do a little bit of substitution while everybody else is calculating the time. And that substitution involves us getting rid of the velocity and putting it in terms of the period. So although I could go ahead and cancel the one r out, we're going to be introducing an r here in just a minute. Now, the interesting thing about this is that this ends up being something that Kepler actually predicted long before Newton or anybody else had put together these rules about the way space worked. Through careful observation, Kepler noticed that there was this, I don't know how you'd say it, this organization to the way things orbited. So he predicted as one of his rules, and Kepler was just a mathematician, that there was a ratio between the radius, the orbital radius of planets, and how long it took for them to go around the sun. And he found this ratio through observation, this r cubed to t squared ratio. What's interesting is that he could only do it by looking at like a handful of planets. When he was doing his work, we didn't see most of the outer planets. Our telescopes weren't strong enough. We could see Jupiter, but Jupiter's orbit was so big that his lifetime would end before he could see it go around the sun once. So it wasn't as though he really had a lot of empirical data, but he was able to show this relationship with the Earth, Mars, and Venus, and just the data that he could observe from looking out into the sky on his own. So one of his Kepler's laws is that there's an r cubed to t squared relationship. And this is also why I wanted you guys who might be a little bit mathy to recognize that you could do this. You could find all sorts of things by just observation. If you sit and count how many seconds it takes for something to go around an object, then you can figure out how far apart they are, or you could figure out the mass. We use this one relationship to basically chart out and figure out almost all of the planets in our solar system, because it tells us a lot from just simple observation. So, although it's not a huge deal that you know this, it is really the orbit equation and can be used for any orbit. It has a cube in it, which makes sometimes finding the cube root challenging, but it'll also tell you the period, it'll tell you the mass of a planet, any one of those things. So, you guys who are mathy, I think it's interesting. Is it ever going to come up? Probably not. So I don't know that it's that big a deal. So we should be about done now. 28 days. Yeah, actually you got something a little bit different than 28 days, didn't you? Put the decimal in the chat real quick, because our answer is wrong. It's not wrong by a lot, but it's still wrong. Now, here lies the issue. If you watch the moon for 28 days, it will go from full moon to full moon in 28 days. But all of you calculated 27. And you think you've done something wrong. And we've done everything as right as we could. There are small things that we didn't do. Like I said from the beginning, we didn't talk about the fact that it actually orbits the center of mass. That adjusts it by about 15 minutes. Not very much, but a little bit. But you might want to know, why isn't it 28 days? And the reason you might find interesting, maybe not, but I hope you will find it a little bit interesting. The reason it's not 28 days is because full moon to full moon is different than the orbit of the moon. We see a full moon because the sun is illuminating part of the moon that we observe. Like right now, if the sun was over here here, let's make the sun yellow. If the sun were over here, we would observe a full moon, because the moon would be illuminated by the sun fully on the face that we see. And that's what makes it a full moon. Now, for us to see a full moon again, the moon has to go all the way around the Earth. But the Earth doesn't stay still. The Earth is going around the sun. So to get to the next full moon, we have to reach a point where the moon has gone all the way around the Earth, while the Earth has moved a little bit to the side, which means the angle of the sun relative to the Earth has changed. So the moon has to move a little bit further in order to be fully illuminated again. It takes 27 days for the moon to go around the Earth, but it takes 28 days for the moon to move that extra distance for it to come back into a full moon state with the sun. So although full moon to full moon is 28 days, 27 days is how long it takes the moon to go around the Earth. So I think it's important that we understand the distinction and the difference, because we're not calculating anything wrong, we're conceptualizing it a little wrong. Not to mention, we want to calculate it right, because if the astronaut gets there a day before the moon's going to get there, that could be a big problem. So they have to know. All right, that was calculating a simple, straightforward orbit. And that should be able to handle all of your questions in homework. Although it's only one example, every other example from this point forward is exactly the same. The only thing is, you are going to get questions where they're going to give you the period and ask you where the orbit is. Things like geosynchronous. Has anybody heard this word before? There's things called geosynchronous orbits. Nowadays, we have so many satellites in orbit, it's like we got a big carpet of satellites on top of us. Elon Musk is launching 100 satellites a month just about to have broadband service in space, or beamed from space. You know, there's lots of satellites that cover us, but in the old days, we didn't have that many. And we had a lot of geosynchronous orbits. I think you probably can figure out what this word means because you know what synchronizing is. When something is in sync, which means it's timed together or it happens at the same time. And geo means Earth. So this is an Earth timed together orbit, which simply means that it stays above the same place on the Earth all the time. So there is a geosynchronous orbit. If you look straight up, there will be a geosynchronous orbit looking right down on us. There's a lot of weather satellites like this. We want to watch where the storm's going, so we have to have a satellite above us all the time. You can't just put that satellite anywhere, though. There's only one place in orbit that is geosynchronous. And what that means is the period is 24 hours. That's what a geosynchronous orbit is, when the period is 24 hours. It just means working this problem backwards now. You're given the period, and you want to work backwards to figure out what R is. That's all it is. The problem is that you can't do it from here. You can only do it from here. Right? Because it's got the substitutions already. You can't find the velocity because you don't know R. So the only way you can find an orbit if you're given its period is to use this relationship. And one of your homework questions is like that. I believe the homework question you had that was like that said that you have an object that's got to be in a 4-hour orbit. And you have to use this to figure it out. So a geosynchronous orbit, period's 24 hours. Any other orbit, and you're given t, you're going to have to use this to figure out its orbit. And there's no two ways about it. It's the only way it works. All right. It's not a whole lot of time left, but there is time for me to answer homework questions. I can do this homework problem for you if you want, or I can answer other questions if you'd like.
Can you do number 5? It's the one with the coefficient of static friction.
Is it the one with the coin on the record player?
Yes.
Okay. So let's have our record and our coin. And although I don't know all the details, they're not really that strenuous. They probably gave you the distance from the center to where the coin is. Now, just a quick look at this from the side. If that's our record, and that's our coin sitting on the record, then you have to kind of imagine that if this is what it looks like, the coin has to be experiencing a force of gravity and a normal force, for sure. But if it's going to be traveling in a circle, remember that without a force towards the center, the coin's going to travel in this straight line if the record is rotating this way. So there has to be a force this way acting on the coin, which means from my free body diagram, there'd have to be a force towards the center of the record, and the only other force available here would be friction. Now, that being said, net force equals MAC. This is a Newton's second law problem because the coin has to be accelerating. And the only unbalanced force is friction. Any question yet? Now, I'm going to draw this a little different because it's probably dealing with the angular speed of the record. So I'm going to put this in terms of angular speed. Makes more sense to me. So we can use either one. Now, In the y direction, the net force is 0, so we know normal equals mg. Right, y direction. So I'd say we were done, except that I know that friction has to be less than equal to mu times the normal force. When I throw that coefficient in there, I know I'm going to be using something like this. So I'm going to substitute like that. That way I keep the inequality, and I like keeping the inequality when we can. So when I substitute over there, I'm going to get on the left side, m omega squared r less than equal to mu mg. And that's why they didn't give you the mass of the coin. I know a lot of people were concerned because you didn't get the mass, and you know, there it is. Is that enough for you to kind of figure the rest of it out? Guys, coin on the record problems, pretty common. Once you've seen it once, you've seen it every single time they're going to ask it. So it's either a coin on the record or a spider on the record or an ant on the record. There are so many questions like that where they just put some object on the record. And it's really, really kind of sucky because none of you have probably ever seen a record before. So, you know, for me, it'll be a kid on a merry-go-round. You know, his butt's got a little friction. If there's not enough friction, you know, he's going to fly off. So do they have merry-go-rounds anymore? You guys know what I'm talking about? The ones that have, like, they look like they get the little bars like that. You know what I'm talking about? If you look at it from the side, it's like, if you find one of these, man, hold on to it like grim death, man. They're taking those away. They're awesome. And they don't like the fact that little kids get their heads stuck like right there and stuff, but I think they're a lot of fun. So it's one of those things where you kind of wait and watch one or two little kids get on it, and then all of you and your buddies get around the edges of it and spin it up as fast as you can so the kids fly off. You ever done that before? You haven't lived until you've seen little kids fly off a merry-go-round. Have you guys ever been to Curtis Hickson Park with all those little spinny rides that are there? There's always some kid getting trapped on one of those and can't get themselves off, because there's the one that you can ride like by yourself just by rocking back and forth. There's always some kid about to chuck their cookies right there. I love it. Kids are stupid, little ones. All right, more homework questions?
Can you do the one that you were talking about earlier, like finishing it up?
Look, earlier was a long time ago.
Like you were saying, like right before we started asking for homework, you're like, do you want us to finish this one or do a different one?
Okay, the one in the homework, I think, talks about an orbit that's 4 hours. Is that right? Is that the one that's in the homework? I don't remember.
It says complete 2 orbits a day.
2 orbits a day? Okay, so they could be changing it for everybody. I don't know. What you have to do is you have to figure out the period from the information they give you. That's probably the hardest part, is figuring out the period from what they give you. So if it's 2 orbits a day, that means it's a 12-hour orbit. Because if it's 2 a day, then it takes one of them 12 hours. You know, I don't really know what time frame you're going to be given. So that probably changes it for all of them. The first thing you got to do is convert that to seconds. So before you do anything else, you know, if it's in hours like that, then, you know, unit multiplier here, seconds, hours, there's 3,600 seconds in 1 hour. So get that sucker converted into seconds. Next, and this is probably critical, if you know that it's going to be the Earth, then you could just use this. It's kind of stock now, and you've got it in your notes. So you're just going to have to take whatever this time is and plug it in here. And don't be too hard on yourself. If you don't know what to do here and you're unwilling to ask, cross multiply. This just becomes 4 pi squared r cubed equals MEG t squared. So don't beat yourself up if you don't know to cross multiply. A lot of kids don't know what they're supposed to do to get out of that. So just cross multiply, and it still looks like a whole bunch of freaking letters. So I understand that for you guys who, you know, the algebra gets to you because it just looks like letter after letter after letter. I understand, and I empathize, but this is what we're up against. So I don't mind not putting the numbers in. You're looking for this. That's your unknown. Everything else is something that you are going to be somehow given. And this is why I told you guys to figure out how to do the cube root. But be careful. I'm pretty sure that this problem asks for the altitude, not the separation distance. So this is not the answer. This is the separation distance. To get the altitude, you're going to have to remember that the altitude is the distance above the surface. So you'll have to subtract the radius of the Earth. And don't, you know, you'll need the radius of the Earth, but 6.37.
It gives you in the functions list on mastering. There's a little
Oh, it
button,
does?
right?
Good.
It's a constant.
Because
You click
it's
it.
escaping me right now, so. All right. If there's nothing else, what I'm going to do is this. We're not going to have the quiz right now. And I don't know if we'll have it first thing Monday morning. That seems unlikely. Bring your homework to school on Monday. I have a few students who have been out. I'm going to open up the mastering for over the weekend because there's a couple of students who have not been able to join us and we've been asked to be flexible. So I'm going to be flexible and just have the homework window open until Monday, but make sure you get your homework done by Monday. We need to finish so we can stay on pace. So Monday, I want to close this out so that we can be done, have a little quiz, if not Monday, Tuesday, but we're going to move on so we can get into work and energy because we want to finish our first part of work and energy by the end of next week. We can do that, but I want to make sure we get all the way done. I want nothing hanging over us when we go to Thanksgiving. All right. I just want to shut my computer off and maybe even leave it at school and not think about work. And I want you to do the same. It's been a hard year. You need to have some time with your family. All right. So it is 9:19, 9:18. I'm going to give you a whole minute. Okay. Unless you're desperate to ask me a question and you can hang out for a few minutes and I'll answer it. The rest of you guys, please enjoy your weekend. I'm sorry I woke you up early on Monday and I'm sorry on a Friday, but I do really appreciate you guys coming in and I will promise to reward your grade for being here. Okay. All right, guys, have a great day today. It looks beautiful out. So go do something fun, I hope.
Have a good one, Mr. Sheldon.
Bye.
Bye-bye, guys. Have a great day. It was great to see you here.
Wait, Mr. Shelton, so the master is gonna be due Monday now?
Yeah, I'm going to open up the window for another couple days.
Okay, thank you. Have a good day.
You too.
Bye.
Bye-bye. Sophia, did you have a question?